We are an unmanned aerial vehicle team established at Kocaeli University in 2021. Our team works in 4 separate departments: organization, mechanics, avionics, and software. This is our competition team. When the competition requirements are examined, the vehicle must take off and land safely and autonomously. A table has been prepared with restrictions, such as avoiding vehicles in the field and completing the task as quickly as possible. For example, it must fly 5 miles in a single flight with a fully loaded weight. The task must be completed in under 30 minutes, and the vehicle must weigh less than 25 kilograms. Many parameters such as vehicle design and avionic components to be used, flight duration, speed, weight are determined in line with these restrictions and the table. Our vehicle is in a coaxial quadcopter configuration. 8 T-motors and 60 A-12S ESCs are used. A 21x6 propeller is utilized. The ESC cables extend to the body through carbon tubes. The motors are interconnected with aluminum mounting components. In the middle section, there is a Pixhawk 4, Jetson Nano, telemetry, RC receiver, and PM07 power distribution board in the middle plate. On the top plate, there are GPS, LiDAR, and 22,000 mAh 6S batteries serially connected. Total capacity is 12S 22,000 mAh. At the bottom of our vehicle, our T-landing gear made of carbon tube, PLA, and aluminum. Under the vehicle, we have drop mechanism operates with a pulley system composed of 5 servo carbon plates and PLA support rods. In front of the task mechanism, our camera gimbal is located and fixed to the lower plate with aluminum mounting components, is situated. A custom gimbal, made of PLA material and equipped with 3 servo motor, is utilized to prevent camera vibration and ensure 3-axis rotation. These servos are controlled via our Dupilot firmware to synchronize with drone movements. Following careful evaluation, we chose the Raspberry Pi HQ camera module for its decent resolution, lightweight design, extensive API options, and strong value for the price, and we use 16mm focal length lens for better resolution. Our model training efforts include 2 CNN architectures, one for shape recognition, trained on images, and another for character recognition, trained on images. Additionally, we've developed a color classification model using logistic regression and integrated a YWello model for ROI detection. We chose objects carefully from about 1,000 images taken by drones to teach the YWello algorithm how to find important areas. We used Python and the CV2 libraries to create sets of pictures for recognizing letters and shapes. For the letters, we used 62 different styles to give our model many kinds of examples. For the shapes, we made them different sizes to help our system learn more about what shapes can look like. Following the identification of ROIs, the captured image undergoes thresholding to isolate the emergent object within. Subsequently, the threshold image is subjected to a k-means method to effectively segregate the text within the shape and extract RGB values crucial for color classification. Finally, we use the text image from the k-means process to recognize characters and the threshold image for recognizing shapes. Our design drop mechanism consists of 5 units of servo motors, 5 PLA spools, 5 PLA rod, and 2 carbon fiber plates. There are parts produced from PLA material to hold the servo motors and the bottles together. The control of servo motors is facilitated by the Holybro PM07 power module. The operation of servo motors at the desired speed and duration has been achieved by programming through their control circuits. The bottles are attached to the rope wound around the rollers. When an object is detected, the servo motors, powered by the PM07 power module, rotate the roller to lower the bottle. Once the bottle reaches the appropriate height, The sharp edge on the roller cuts the rope, ensuring the bottle reaches the target accurately and safely. For the task, NVIDIA Jetson Nano has been utilized, with its integrated camera connection directed to the appropriate port. Signal connections of the servo motors are directed to the Jetson Nano, while the power connections are made to the relevant pins of the Pixhawk 4. Our drone's Pixhawk 4 utilizes a 360 degrees LiDAR to prevent collisions with objects, transmitting data via serial communication. GPS data is conveyed to the Pixhawk via CAN communication. For image detection, we employ an NVIDIA Jetson Nano and Raspi HQ. The Jetson Nano sends the detected image's position to the Pixhawk 4 via serial communication in Mavlink packets. Additionally, PWM signals for the bottle-dropping servo motors are provided by the Jetson Nano. Communication between the ground station and the Pixhawk 4 occurs through serial communication using RFD 900X telemetry modules, while communication with the safety pilot is via RF communication utilizing the 2.4 GHz bandwidth between the FlySky IA-10B receiver and the FlySky i6X transmitter, employing the AFHDS2A protocol, with signal strength monitored through received signal strength indication. In the designed vehicle, a coaxial quadcopter motor arrangement was preferred. The mechanical parts of the vehicle are made of aluminum, PLA, and carbon fiber. The carbon plates and aluminum parts were obtained using a CNC cutting machine. Aluminum and 3D printed assembly parts have been used in the landing gear. The vehicle has a wingspan of 5.8 feet and a height of 1.509 feet, with a mechanical weight of 5,042 grams. The motors are supported by aluminum linkage parts and carbon fiber tubes extending from the body, which are 400 millimeters in length. Aluminum parts have been used for the connection of the arms extending from the body to the motors. Tight fit and bolt connections have been employed to prevent vibration and ensure stability. It has been determined that 8 units of MN 6007 2160 kV motors and 21-inch long, 6-inch wide propellers are suitable for use. The motors, which produce 12.87 pounds of thrust, have a power rating of 1120 watts and draw a current of 23.7 amps. 26S 22,000 mAh LiPo batteries have been used as the power source in the vehicle. These batteries provide a flight time of 20 minutes. To protect the system from excessive current, it is safeguarded by a 160A megavalve fuse. The power from the batteries is directed to the power distribution board, from which both the ESCs and the Pixhawk 4 are supplied. The ESCs are connected to the power distribution board for the energy required by the motors. According to our calculations, these motors provide 77.206 pounds of thrust to our vehicle. The motors are connected to the body of the drone with an 8 degrees tilt, aiming for a more stable flight. When we compare the thrust with the weight of the vehicle, it has a thrust-to-weight ratio of 2.68. Our drone reached a peak altitude of 105 feet without any connectivity issues. During 6 autonomous flights totaling 120 minutes, we set 352 waypoints, adjusted turning radius to under 100 feet, and maximum deviation to 3 feet. Our success rate was 92%. Our maximum altitude limit is 105 feet. It completed 23 flights, 17 manual and 6 autonomous, with 10 fail-safe landings. The longest flight with payload was 11 miles, and without payload was 9 miles. Performance data: timeline 100%, imaging and autonomous target recognition, ODLC, 86%, obstacle avoidance 82%, autonomous flight 92%, overall success rate 90%. The bendy ruler is an algorithm developed by Ardupilot and is used for obstacle avoidance in autonomous vehicles. We use the YD LiDAR G2 on the vehicle. The algorithm is typically described as a 2-stage process. Firstly, initial positions are determined and objective functions are defined. In the second stage, The flexibility of the ruler is simulated to rearrange the positions of objects, and the objective function is minimized or maximized. The algorithm operates by bending a ruler and adjusting the positions of objects accordingly. The bending of the flexible ruler affects the objective function value by altering the distances between objects. Through research and analysis, it has been identified that there are significant differences between the initial and final stages of design. The presence of 6 arms and the width of the plates in the previous design increases the vehicle's weight, while the excessive arm span in the old design complicates vehicle control. Considering these factors, a 4-arm coaxial configuration has been preferred. The team has reviewed potential risks and made appropriate plans accordingly. Fiber nuts have been used to prevent detachments due to vibrations in mechanical equipment, and the vehicle connections have been checked multiple times before flight. A failsafe mode has been defined in case of disconnection between the vehicle and the ground station during flight. Personal protective measures have been taken to prevent injuries that may occur during production. Pilot certificates have been obtained for both Turkey and the United States to ensure flight safety. As engineering students from Kocaeli University, our team of 17 members has created an 8-motor coaxial quadcopter drone with features including image processing, advanced autonomous flight, and obstacle avoidance capabilities. We are thrilled to participate in the competition as the Storm UAV team.